Hi guys, welcome again to Math 135. Today we are doing section 1.9 and this is the last section for chapter 1 on graphs and functions. That means after today we are finished with chapter 1 and we're moving on to bigger and better things. After this section is done, we're going to start reviewing and then we've got an exam coming up for chapter 1. Okay, number 1 topic for today, determine whether a function is one-to-one. And to do that, we basically can apply the horizontal line test. We can do that with an actual graph, or we can do it just looking at the inputs and outputs. And this is important because a function is one-to-one if it's invertible, if there is an inverse. And if a function is one-to-one, that means then there is an inverse. So this whole section is mainly about inverse functions. So we need to start by knowing whether you can find an inverse at all. And that's why we need to know if it's one-to-one or not. Okay, number 2, determine if a function is an inverse by applying the inverse function property. So for that one, we're going to be given a function and another function. And then you're going to basically check, does it satisfy this property? If it does, that makes it an inverse. If not, it's not an inverse. Number 3, we're going to find out how to find and graph the inverse of a function. And then number 4, determine the domain and range of a function and its inverse. And it turns out the domain of a function is the range of its inverse, and the range of the function is the domain of the inverse. So it's kind of interesting if they're opposite like that. Okay, anyway, this first video is about number 1, how to determine whether a function is one-to-one or not, and then apply the horizontal line test. So what makes a function one-to-one? Well, it's one-to-one if every time you have a y value, there's only one x value. Easy way to think about that is there's no repeated x value. I'm sorry, no, I said that wrong actually. There's no repeated y values where you have two different x values and a single y value. The other way to think about that is to think about the horizontal line test. Horizontal line test. Now, I don't know if you guys remember, but remember when we first talked about functions? The way that we defined a function was that it was a relation where every x value, hold on, I want to use a pen. For every x value had only one y value. And when we were checking if something is a function, we maybe sketched its graph, and then we said, okay, if you draw a vertical line anywhere, and anywhere you draw that vertical line, it only crosses once, then you have a function on your hands. On the other hand, if you have something like this, where a vertical line crosses at 2 spots, then it's not a function. Well, it's a very analogous thing going on here, right? If I have some function, I know it's a function, but if I draw a horizontal line and that horizontal line crosses more than once, then it's not one-to-one. But on the other hand, if I have some function and any horizontal line only crosses once, no matter where I draw that horizontal line, then in that case, you do have a one-to-one function. Okay, so that's the definition of one-to-one and the horizontal line test. Now, I mentioned this in passing, but it's important to note here, if a function is one-to-one, then that means it has an inverse. And that's important because this whole section is really about inverses. All right, let's try questions 1 through 7 right now. And I have them copied down here. Starting with number 1. Determine whether or not the function is one-to-one. Easy check. Think back to that picture, remember. If it fails the horizontal line test, it's not one-to-one. So think of it as if I have 2 spots with the same y value. So how do I look at that? Here I have a set of inputs and outputs, right? Here's the x values and the y values, x, y, x, y. So what I want to check is is there any y value that occurs more than once? So looking at these guys, nope, they're all different. Since they're all different, then yes, it is one-to-one. Okay, number 2, do I have any y values that repeat? And yes, right here, I've got -2, 4. So think of this as, if I was to graph this, -2, 4 right here, and +2, 4. So horizontal line would go through both of those points, right? And so that means it's not one-to-one. It's not a one-to-one function. So no. Not one-to-one. Okay, moving on to numbers 3 through 7. For these guys, we're going to sketch the graph and then determine whether or not the function is one-to-one. Starting with number 3, I've got f of x is x squared minus 3x. Okay, you know, right away, as soon as I see this thing, I know it's a quadratic, and quadratics are going to look like this, basically. They're going to have that U shape, or sometimes if it's a negative in front of the x squared, it's going to have that upside down U shape. And that's going to right away tell me, okay, a horizontal line crosses twice, so it's not going to be 1 to 1. But, you know, we should just get practice graphing this thing a little more accurately because we've learned about this before. We learned how to deal with x squareds and then also their translations. Except this guy doesn't look exactly how we want it to look, right? It doesn't have that format that we have, like the x minus h plus k, blah, 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 that whole thing. It doesn't look like that. So I have to make it look like that first. And the first thing I'm going to do is instead of writing f of x, I'm going to just replace that with a y because when I graph it on my coordinate plane, I'm thinking of that f of x value as a y. And the second thing I want to do is I want to just complete the square. So how do you complete a square? What you do is you always look at this term that has the x in it, and you half it and square it. So half of 3 would be 3 halves. And then square it. So 3 halves squared. And I'm going to do it, if I do it to one side, I've got to remember to do it to the opposite side as well, or my equation is no longer true. So now it's still true. And 3 halves squared, that's going to be 9/4, right? So, oops, I meant to write this. Y plus 9/4 on the left. And this right side, I'm not going to change that to 9/4 because what I'm going to do, I'm going to take this whole piece and change that to its squared form. What's its squared form? Well, this is a minus, so this should be a minus. And I'm just going to input that number, 3 over 2, and square it. That's how we complete a square. If you don't believe it, then just, do some side work over here and just multiply x minus 3 halves by itself and you'll see what comes out. But it works because this part gets multiplied by itself. That gives me the 3 halves squared, right? And then x gets multiplied by itself. That gives you the x squared part. And then you got 3 halves x and another 3 halves x combined together to get negative 3x. So it does in fact work. Okay, last thing I'm going to do is just get this 9/4 out of there. So I'm going to subtract it on that side. If I subtract it on that side, I got to do the same thing over here. So the end result is going to be y equals to x minus 3 halves squared minus 9/4. Now when I go to graph this thing, what does that mean? That means I have a quadratic, but it's shifted 3 halves to the right, 9/4 down. So here's 1, 2, 3 halves would be right around here, right? And then 9/4 down. 1, 2, 9/4 is just a little past 2. So here and here, it's the starting position. No other transformations, so it's gonna open up basically something like this. Okay, I just drew a very rough sketch for that. I don't really care about the points. I just care what its overall shape is, and the fact that a horizontal line, just like we suspected, would cross through 2 points. Because a horizontal line crosses through 2 points, that means it failed the horizontal line test, and because it failed the horizontal line test, that means it is not 1 to 1. So number 3, not 1 to 1. And we graphed the thing. So no, not 1 to 1. Okay, number 4. Okay, number 4, absolute value. As soon as I see absolute value, I know it's going to have this general V shape, right? No? Oh, wow. I didn't know we could do that. Okay, general V shape. And so a V shape is going to it's going to fail the horizontal line test too, right? It's going to cross at 2 points if I draw a horizontal line. But let's graph the thing. This is just a shift of 2 to the right, 1 up. So my y-axis is crooked. Y-axis, x-axis. I'm moving 2 to the right, 1 up. Graph the thing. Here's the starting position. Graph the V. It looks like this, right? Now, if I draw a horizontal line somewhere over here, it crosses twice. Now, by the way, I could draw a horizontal line over here and it would only cross once, but that's not the point. That's not important. If there's anywhere I can draw a horizontal line that crosses more than once, then it fails the horizontal line test. And it does, in this case, fail. So it's not 1 to 1. Just as we suspected. Yeah, V shapes fail. Okay, number 5, cube root plus 2. Cube, what do cube roots look like? Those are our good friends too. Remember cube roots? they look like, cube root of 0 is just 0. Cube root of 1 was 1. And cube root of -1 was -1, like this, right? So cube root should look something like that, where it kind of decreases forever, goes to this point, crosses the middle, and then increases forever. Oh, no. Shucks. I was drawing it so good, and then you had to autocorrect me to a line. I don't want a line. Okay, something like this, right? Except this one is a +2. No big deal. That's just a shift upwards by 2. So shift 1, 2, something like this. But same shape. Same shape, meaning if I was to draw horizontal lines, none of them cross more than once, no matter where I draw them. So in this case, it passes the horizontal line test, meaning yes, it is 1 to 1. Beautiful. All right, number 6. Number 6, x cubed minus x. Now, word of caution here, guys. Word of caution here. You know, when I was first thinking about this, right, like off the top of my head, I had a sort of weird, wrong intuition. Because remember, the regular x cubed function looks something like this. I don't know if you remember that. But that's not the general form for something with a cube. I'll show you what I mean. So this one, whatever this power is, that kind of tells you the number of possible roots. And what's a root? Root is just where it crosses the x-axis. Now, if we have a function that crosses the x-axis more than once, then for sure it's going to fail the horizontal line test, right? Well, let's see how can we make this look like something that's easier to graph. Well, the easiest way to do that is to factor out an x first. So, you know, actually that's a bad spot to do that. Let me put this over here. Okay, so I'm going to draw that same function. Y is equal to x cubed minus x. And easiest thing first to do is just factor. So I'll pull out an x. That gives me x squared minus 1. And oh, x squared minus 1. This is an old friend from algebra. Guys, it's a squared minus 1. And 1 is also something squared, 1 squared, right? So this guy becomes x plus 1, x minus 1. Anytime you have something squared minus something squared, remember a squared minus b squared is equal to a squared plus, I'm sorry, no, I mean a plus b, a minus b, right? That's exactly the situation we have here. Exciting. Okay, so looking at this thing, those are different roots, right? Those are 3 spots where if x is 0, then y will be 0. Or if x is 1, then y will be 1. Or if x is -1, then y is going to be also 0. I think I said the wrong thing. If x is 0, it's going to be 0. If x is -1, it's going to be 0. If x is +1, it's going to be 0. So when I graph this thing, at -1, I'm at 0. At 0, I'm at 0. And at 1, I'm at 0. So already I know it's going to fail the horizontal line test. Now, the general format for this guy, you know, when you're trying to graph this thing, it's going to look either something like this or something like this. But it's going to go to the right upwards, I know. I know it's going to end up upwards because when this is something large, this is something large, this is something large, it's going to be positive, right? What you can do in general, guys, is check the signs in between, right? If you do large value, that's here, this is 1. If I do x that's bigger than 1, it's positive, bigger than 1, positive, bigger than 1, positive. So 3 positives make a positive. So this guy should be positive to the right. Here, if x is between 0 and 1, somewhere here, like a half, this would be positive. This would be positive. Half minus 1 would be negative. So 2 positive negatives make a negative. So just like I thought, this was negative down here. If you're over here at -1/2, this will be negative. This would be positive. This would be negative. So 2 negatives and a positive make a positive. So just like we thought, this is above the axis here. And then when the x is negative, like 2 or something, that's negative, negative, and negative 3 negatives make a negative. So down here, it's negative. So just like I suspected, that's the general shape of it. Okay, now looking at this graph, there's a whole bunch of spots where if I was to draw a horizontal line, I hit more than once, right? And in fact, right at the x-axis, I hit 3 times. So it fails the horizontal line test, meaning no, not 1 to 1. Okay, finally, the last question for this video, number 7. And we've got another one of our old friends now. Y is equal to 1 over x. Y equals to 1 over x. And this is something that we should be familiar with how to graph now. Okay. Oh, that was crooked, sorry. There you go. Here's x, here's y. And the graph of 1 over x, remember, it gets closer and closer to the asymptote at the center, and then closer and closer to the line 0, or the x-axis. And then on the other side, it's the same thing but negative, right? Like this. Okay, so looking at this thing, there's no spot that a horizontal line crosses more than once. Obviously, over here, it's not crossing more than once. Now, when it gets really close over here, it looks like it might, like a horizontal line might cross more than once, right? But that's just because my drawing is inaccurate. In truth, this guy here is getting closer and closer and closer to the x-axis, and it's always getting closer. It's always just getting slightly closer. Even if it's like an infinitesimal amount, it's always moving upwards. So that means there's never a spot where I'm going to draw a horizontal line and it's going to cross at the exact same spot 2 different times. Which means this time it passes the horizontal line test. So yes, it is 1-to-1. Which means it's also going to be invertible. And you know what? Fun fact, guys. This guy happens to be its own inverse. One of those few occasions where it's its own inverse. All right, that is it for this video. I'll see you in the next one.